Imagine that you're walking in the hills, but a heavy fog has descended and you can't see where you're going. Visibility is just a metre or two in front of you. Moreover, you've lost your map, you've lost your compass, and you don't know where you are. However, you do know that base camp is in the bottom of the valley. What do? Well, looking around your feet, you can tell which way is downhill. At least you hope you can. And so you can just walk downhill, and with a bit of luck, you'll wind up back at base camp. This is the classic metaphorical basis for gradient descent methods, which we mentioned in the introductory lectures last week. If we can't find our minimum point analytically, we'll have to sneak up on it or down on it by taking steps until we get there. Provided we can calculate a gradient at all, we can search incrementally in that direction. As long as we're going downhill, we must be getting closer. If the problem happens to be convex, then we pretty much have to find our way to the minimum eventually, or at least get arbitrarily close to it. This is the algorithm for classic batch gradient descent. We start somewhere at some arbitrarily chosen initial position. We calculate the local loss gradient with respect to the entire training set. We take a small step down the gradient. We have a look to see if we're there yet, and if we're not, we do the whole thing again. This is a very slightly more formal pseudocode explanation of that algorithm as it appears in your lab exercises this week. Batch gradient descent is the basis for a whole range of methods, and it's a really good starting point for finding your way to an optimum. It has a number of issues, of course. First of all, you need to choose a learning rate, that is, the step size that you're going to take at each iteration. You need to choose your initial position, where you're going to start out from. It turns out that this can make a big difference for certain classes of problems. It may be slow to converge. If your gradients are very shallow, then you'll have to take a very large number of steps before you get anywhere near to the minimum point. For non-convex problems, it can get stuck in local minima. And also, it can be prohibitively expensive for very large data sets because you have to calculate your loss gradient for all of the samples in your training set. One simple approach to get around this latter problem is something called stochastic gradient descent, where instead of calculating the loss gradient for the entire training set, you do it in very small stages, in fact, for one sample at a time. The algorithm is extremely similar to the batch version. You start somewhere, you process a single training example, you calculate the gradient, you take a small step down it, you check to see if you're at your destination, and if not, you repeat with a different sample from the training set. Stochastic gradient descent still requires you to choose a learning rate and an initial position. It is not as expensive as batch gradient descent because you don't have to process the entire training set before every update. So it tends to progress more quickly, but the progress might also be much noisier. If processing updates for your model is slow, then you can spend a lot of time updating for each small amount of information acquired. The middle ground here is something known as MiniBatch gradient descent. In this case, you don't process the entire training set at once, but you may process more than one sample at a time. You divide the training set into small chunks of some chosen size. You process each one as if it was your whole training set, do the update, and then move on to the next chunk. This can be a good compromise between the very smooth but very expensive updates of full batch gradient descent and the noisier but cheaper updates of stochastic gradient descent. Of course, the batch size that you process at a time is another hyperparameter that you have to choose. Some form of MiniBatch gradient descent is extremely widely used, especially in deep learning. In plain stochastic gradient descent, each update is fully determined by a single sample. On average, over the whole population, you would expect samples' gradients to be pointing in roughly the right direction, but individual samples may be pointing all over the place. Even if the data is not noisy, there can be issues if the steepness of the gradient is drastically different in some directions than others. You'll wind up having to balance the learning rates for the gradients in different directions, which can lead to either incredibly slow progress, because you've chosen your learning rate very small, or oscillatory behaviour in the steeper directions. A popular improvement to gradient descent methods is to add the notion of momentum. In this case, we keep a kind of weighted running tally of recent updates. Consider this as a velocity. We retain some, usually a lot, of this velocity from update to update as a kind of consensus on the directions that the majority of the samples seem to be agreeing are the right ones to go in. At each update, you add a modest contribution from that particular individual sample. Using momentum can reduce noise and oscillations and speed up convergence. In some cases, it may also help to escape from local minima. Two of the issues with vanilla gradient descent methods are that you have to choose your learning rate, and also that the learning rate is global. It applies equally to all of the different feature dimensions. If there is a significantly different rate of change in the different dimensions, then you'll either be taking much too small steps in some of them or much too large steps. There are a variety of more sophisticated versions of gradient descent which attempt to address these problems. These are algorithms like AdaGrad and RMSProp and ADAM. These are methods that adaptively scale the learning rate according to the variance in the feature dimensions that they've observed along the way. They generally maintain a separate scaling parameter for each feature dimension. If you have a lot of feature dimensions, then this can increase the number of parameters in your model substantially. All of the gradient methods discussed so far are first-order methods. They only make use of the first derivative of the loss function. More complex second-order methods also make use of the second derivative to speed up convergence considerably. The archetypal second-order method is Newton's method, or in the vector function case, Newton-Raphson, which makes use of the curvature of the function to set the learning rate. If the gradient is changing very slowly, then you can afford to use a bigger step size. If the gradient is changing very fast, so the curvature is very high, then you must choose a smaller step size. Newton-Raphson requires calculating and inverting the full Hessian matrix of second derivatives. This can be a computationally expensive or impossible process. If you have d features, then the Hessian will be a d by d matrix, which you have to invert. For 10 features, that might not be unreasonable. For 3.5 million, it starts getting a bit out of hand. Newton-Raphson converges much faster, that is to say, in many fewer iterations than ordinary first-order gradient descent. But each individual update is much, much more expensive. To somewhat get around this, there are a number of other methods which are known as quasi-Newton methods, for example, BGFS. These methods avoid calculating and inverting the Hessian directly. Instead, they attempt to iteratively approximate the inverse Hessian itself using the gradients encountered at each step. Quasi-Newton methods are more complex than Newton's method, but they're also a lot cheaper. Gradient descent methods are really the bread and butter of machine learning, and you're going to see them a lot. You'll be implementing vanilla batch gradient descent in this week's lab exercises as a tool for implementing logistic regression. For the specific case of logistic regression, practical implementations, such as you'll find in scikit-learn, tend to use second-order methods instead, but first-order methods are certainly viable for the sorts of toy examples that you'll be doing in the labs. For more complex models, like deep neural networks, the adaptive first-order methods, like ADAM or RMS-Prop, tend to be used together with momentum.